push Relabel algorithms. And which you can think of it as MacFlow algorithm, like how to compute MacFlow algorithm using the type H data structure that we learned about from last week. Yeah. And my hope is to cover 3 things. Let's see if we can do it. But we're going to see how to do it in MN time in unit capacity graph. And it's going to be slower in capacitated graph, but then we speed it up to MN, basically. Yeah. Okay. And again, the notion that I want you to be aware of is the notion of residual graph. Okay. When you have a graph G and a flow F, then residual graph is just kind of the graph that such that it basically says for each edge how much what's the remaining capacity to send flow on each edge. For example, like if you have a graph G and then the G of F, the residual graph with respect to F, is such that look at any edge in G, then you create an edge in GF with this capacity. So the total capacity minus the flow that you already send. So you can send through an edge E again by this much capacity at most. And also you create a backward edge, E backward, where the capacity for the backward one is the flow on an edge. It means that you have budget to cancel this much flow. Okay, that's the intuition. Yeah. And basically, this is how residual graphs look like. Okay. And okay, I will skip all this because we talk about. But the point is that if there is no augmenting path remaining in the residual graph, then the flow or the pre-flow is already maximum. Okay. And actually, anyone recall what is pre-flow? Yeah. At least intuition. Yeah.
Like you have some flow, like it doesn't send everything from the source. Like it gets stuck somewhere.
Yeah, it kind of get like you try to send flow from the source, but it doesn't send fully, it doesn't reach the sink yet. Yeah. But the way that we formalize it is just that it's just a vector F such that the flow out of F is at most the source at the flow out of F at any node. The net flow at any node V is at most the source from V. So we never send more than the source. But the intuition that kind of capture that we don't send the flow to reach the sink yet is that there can be some residual source at a node. Or this is like excess. Excess at node V can be more than 0. Okay? Okay, so now, okay. And recall the type H data structure that we had from previous course, previous week. We have a graph and labels, and we want to maintain the active or admissible edge. Okay, what's the point of active one? It's basically try to model it's basically the set of type edge. Yeah, we want to maintain that, and but the input can undergo updates, which is to relabel, increase the label, or to update edge, that is to insert an edge, or to delete an edge, or to insert some edge. But any edge that we insert cannot be overstretched. It's always relaxed. Okay. So this data structure only what will happen is that we only have relaxed edge. Every edge is relaxed, and the active set is just exactly the tight set. Okay. So that's my recap. We're gonna start now. Okay. So, okay. And this tight edge data structure takes mh plus u. Okay. M is the number of edges, h level, like maximum level, and u is total number of edge update. Okay. All right. So now let's look at push Relabel algorithm. Okay. It's an algorithm that you have a graph and you have parameter h. Okay. And you should think of h here as like how much, like what amount of attempt that you want to try to send flow. The more, like the larger h is, like more attempt you try to send flow. That's the intuition about h. But it's going to be the same h in tight edge data structure. Okay. And now, okay, we start with initialize our label to be 0. The flow is just 0. And here's the important thing. We maintain tight edge in which graph? In residual graph. Okay. Not in the original graph. This is residual graph. And when we have tight edge, we need to set edge weights, right? The weight of each edge here is just going to be all 1. Okay. Right. Okay. Good. So now, let's say that this E prime F is just all edges in the residual graph. Maybe call this EF here. This is all edges in residual graph, which is a subset of this thing. Only the one that is tight. Okay. That's E prime F. Okay. So what the algorithm will try to do is just this. As long as there is an active node, U, what does it mean to be active? It means that like you have level from 0 to h. Think like h as like this is 0 to h. Okay, everything start at level 0 in the beginning, and then it will the level keep increase. Once the level reach h, then we say it's dead. It's basically reached the maximum level and it cannot go further. This is like dead zone, if dead zone. Okay. But the node is active only if the level is less than h and it has some excess on it. Which makes sense because if it has excess on it, we want to forward the flow. Okay. So just look at the guy that's not dead yet and have something to send. That's active. And if it's active, then we just look at a tight edge out of it. So suppose that this node U is here. Maybe the level is like 10. Okay. Then it just look at edges that is tight. When it's tight, then it means that the level here need to be, this level need to be exactly U minus 1. Right, because all of the weight here has level, has length 1. So if it's tight, then it's tight in this direction. So the tight edge go in this direction. Go kind of downhill by one unit. Okay. So look at an edge that is tight, E, and then push. we try to send flow through an HE. Okay. By how much? Let's look at this. How much do we augment through the edge? First, we will not augment by more than what we have, what the excess that we have. If I have excess of 2 units, I don't want to send more than 2. Okay? So that's, I send at most my excess. Second is that I send at most the residual capacity of that edge. For example, if my excess here is 5, and the residual capacity is 3, then I just send 3. This just means like, yeah, how much flow can you send through this edge? Okay. Okay. Then once we have this, then we just send flow by C augment, which means that the remaining capacity of this edge will reduce by C augment. Make sense? Yeah.
So could we if like that one had 5, right? Could it be like first time it pushes 3, then it's 2, and it gets picked up again and sends the remaining 2?
It could, like for example, like someone might send flow to you, and the excess might increase. Okay. Yeah. So like you might need to send flow many times. Yeah. Okay. But by the way, like once suppose that I send 5, I send 3 through this edge. This will become like saturated, and like once it's like the residual capacity will become 0. Suppose that I send 3 in this direction. Residual capacity becomes 0, then it becomes basically removed from the graph. So this edge will not be there. Okay. Okay. So we have this one. Okay. And the way you think about like, but note again that each edge in the residual graph can be forward edge or backward edge with respect to original graph. Okay. So you can think like if this edge is actually the forward one, is from the original edge, then we really just send more flow along this edge. But if it's actually backward, when we send flow through this edge, it means that we reduce the flow by this much. Okay? But you don't need to think too much about this. This is just kind of like without case here. Like you just look at residual graph, send flow by C augment, then the residual capacity reduce. Okay. So as long as there is some tight edge to send flow, send. If there is nothing to send, like if there is no tight edge from you, then we just increase the level. Okay. We only try to send flow along tight edges. Question?
What's that the intuition for only sending from tight edges?
Good. The intuition is that you see like we know before that tight edges are edges along shortest path. And we want to try to send flow through short path so that it reaches to the sink as fast as possible. Okay, that's the really like clear intuition. We don't want to send flow like anywhere so that it doesn't reach to sink. As long as we send flow along shortest path, it should reach sink as fast as possible.
This is like to make the runtime faster.
Yeah. Yeah. Okay. Good. So that's it. That's the algorithm. As long as there is an active vertex, something is not dead and it has some excess, send. If it cannot send, if you cannot push flow, relabel. Keep doing this until you cannot do. Meaning that, suppose that until you cannot do, then you return the flow, and return the label too. Okay. So there are like two cases, right? Suppose that at the end, suppose that no vertex is dead. No vertex reached level h. What does it mean? It means that every node has no access. When there is no access, we are done. We really send out the flow successfully. But otherwise, there will be some excess. But excess, where can it be? At the node of which level?
The dead ones?
Yeah, at the dead one, the level h only. Okay? So the excess, at this point, if we didn't send out the source from to sink, then there is some excess only at level h. Okay, good. So that's push Relabel. And my claim is that if we just run push Relabel algorithm with level, like maximum level, h equals n plus 1, it's gonna return us max flow. That's the, yeah. Okay. Question about the description before we analyze it. Okay. Okay, so before we really show that it's correct, I need to show that this is at least valid. In what sense? In the sense that, you see, our type H data structure requires some invariant, right? Which is, it requires that all edges remain relaxed. Why is it the case that, like, the way that we update this residual graph, every edge remain relaxed? You see, like, every time that we push flow, we change the residual graph, right? But we need to say that every edge remain relaxed. Okay, so first, when we relabel, if we increase the level, some edge could be stretched. But I claim that it never overstretch any edge. Why? Because we relabel only when, like, we relabel U, we increase the level of U, only when there is no tight edge out of U anymore, right? There's no tight edge out of U. So every edge, like, that is kind of out of U, they are all, like, kind of over relaxed. So even if we increase the level, it's still relaxed. Okay. Next, how about push? So consider when we push. Suppose that this is an edge, E. Okay. And this is a tight edge. Out of U. Okay. And this is the edge in the residual graph. So, and it means that this level, maybe this level is, this is the level, here is level U, and level here is like, it's just need to be U minus 1, level of U minus 1. We have that if this is tight, if we push flow from U to V, it means that this is tight, and the level here is like just one more than this one. Okay. What happened when we push flow? Well, it means that like we might delete this edge after we push flow. When will we delete this edge? How like, is it always the case that we will delete it? And if we delete it, when that will happen? When would that happen?
When it's like saturated, when it's
Exactly. When we saturate it, that's when we delete it. Okay. But deletion is just a safe operation. Deletion never create a new edge that is overstretched. So that's totally okay. Okay. So that's when we might delete this edge. But at the same time, when we send flow from U to B, that create actually like an edge B to U. Because now if you send flow from U to B, you could have cancel flow in like send flow backward. So you create this edge B to U. But is this edge overstretched? Clearly no, because if like it will be stretched only if like like the level here just go further to this direction by more than 1. But here it even go in this direction. So it's not stretched at all. It's even zero, like better than zero stretch, better than zero relax, right? Okay. So each of the push operation is a safe operation. It doesn't create any overstretched edge. Okay. Okay. So this is good. Okay. This is just what I discussed. Now the next thing I want to say is that F here is always a preflow, meaning that the net flow out of U for every node is at most the source at U. Okay, but that is kind of easy to see. So, I mean, when you have a node U, okay, and then you push flow, okay, you push flow by at most by like C augment, okay, but C augment is basically at most the excess and also the residual capacity. So C augment, the flow that go out of U is at most the excess. Okay. So if you think like this is like maybe this is like 0 and this is the total flow at U, and like we want to say that the total net flow out of U is, this is what we want to say, right? The total net flow out of U is kind of don't exceed this thing. This is what we want to prove. Okay. Okay. So now you know that suppose that F out is at least right now is here. Okay. And we know that after push, it might increase. F net flow might increase by how much? By at most this much. By at most the excess at U. But the excess at U is at most the difference between source and F out. Just from the definition of excess. Okay, so it could increase by this much, by something here, but the green thing here, which is excess, is the green thing is like the size of the green thing is at most this much. So it cannot, like, even after push, you cannot exceed the data of U. Okay, make sense? Okay. So that's why like you maintain this one. It's always a preflow. Okay. So now we see that this algorithm is valid. We now just, it will indeed like, it's well defined. Now we just analyze the output. Okay. So what I will now analyze is like, suppose that we set h to be n plus 1. Then let's see that f here is maximum. Okay. Good. So to say that f is maximum, all I will say is just this. When h is n plus 1, I just say that at the end, there is no augmenting path left. What is augmenting path? It's a path from residual graph from access to residual sink. I'm just going to say that there is no way to send from access to residual sink. That is, you cannot increase the amount of flow. So if that's the case, then f is maximum. So we can prove this. Okay. So the idea is that I'm going to say that here's the idea. You have level 0, okay, and you have level h, which is n plus 1. Okay. Now, at the end, we just argue that if there is some excess left, this excess needs to be at level h, right? All the excess is at this level. Because otherwise, if it's here, then it's active. We didn't stop. Okay. So this is good. All the excess is at this level. And I'm going to claim that our residual sink is at this level, at level 0. Like I can claim that any node that has residual sink, like it can, any unsaturated sink, any unsaturated sink, like the one that residual sink is more than 0. This one is always at level 0 from the beginning until the end, actually. Okay. This is where like unsat sink is at level 0. Suppose that this is true. Why can we say that there is no path from access to sink to unsaturated sink?
That just come out of like our tight edge data structure? Like that was, we had a similar argument for shortest paths as well.
Yeah, it's going to be really similar. Yeah. So do you see that an edge here? Here. Every node here like the level, because every edge is relaxed, right? So the level of U is going to be at least the distance from U to, let's call this thing like all the node at level 0 LU. Okay. The level of U is at least the distance from U to level 0. Why is that?
So wait, if something's at the excess, then it's like shortest path to the sink should be n plus 1 nodes away, right? But you can't have n plus 1 nodes because
Exactly. Suppose that you believe in this one, then you see that it means now that this shortest path from excess to unsaturated sink is at least n plus 1. But if there is any path at all, the distance needs to be less than n. So it means that there is no path. But that assumes that you believe here. You believe that level is at least the distance to level 0. But can anyone say at least intuition why again? Why this is true?
I thought the level is at most because like the worst case is if it's all stretched, then it's equal to the distance.
Yeah.
See how it can be bigger.
It cannot be bigger. I mean, actually, it can. So because some node might not have tight edge out of it.
Oh.
If every node have some tight edge out of it, then the level is going to be at most the distance. But right now I just said that all edges are relaxed, but some node might not have tight edge out of it. So you only have this lower bound. But to see this one, right? Let's say that there is some path here, such that the distance is less than the length of the path is less than the level. Okay. But it now just means that some edge along this path need to be overstretched. That's it. Right? If there is some short path in this way, but my level is at this level, it's kind of far. So some edge it must be overstretched, but there is no overstretched edge. So it means that any path here need to have length at least level. Good. So do you believe that once we can prove this, we are done? Questions? Is everyone agree with this one? Okay. So why is it the case that the unsaturated sink is always at level 0? Well, first, the argument is just here. Once a sink is saturated, it will never become unsaturated again. Because we only push flow out of some node. Suppose that T is a sink that is saturated, right? So then even if T is a sink, suppose that C is a sink. There is some sink here, okay, sink at T. And at some point, this some guy send flow, and this is saturated. It can be the case that some other people might send flow to V again, and it just gonna create excess at V. But when we try to send flow out of T, yeah, some W might send flow to T again, and it will create some excess here at T. But when we try to push flow out of T, we only push excess out of T. So the thing that the part that is saturated, the sink part here, remains saturated. Okay. Good. And also every unsaturated sink is never relabel. So, and if it's never relabel, it means that the level remains 0. Okay? So why is that? I mean, it could be relabel only when it has access. Okay. Yeah. Like, so if sink is not saturated, then it has no access. So like basically for each sink T, it might start with like some unsaturated sink. And whenever the sink is saturated, suppose that you send flow here. If it's saturated, then like you might relabel it. But the guy that is not saturated yet, like it will never have access, and you will never relabel it. So the level is always 0. So the guy that has the sink that is unsaturated just have level 0 from the beginning to the end. Okay. All right. So once you have this, then basically now you get that the distance from S to T from the unset source to unset sink is at least h, which is more than n. But it just means that there is no opening path. So f is maximum. Okay. Good. That's it. So the point is just we make sure that we stop only when there is no opening path, basically. Okay. This is where we need h to be more than n. If h is n or less than that, it could still remain some opening path, and we cannot say that the flow is maximum. Okay. Now let's analyze the time. So, okay. I will show 2 things. I will show that just look at this algorithm, push the level up to level h. The running time is just going to be mh in unit capacity graph and mh square in general. Yeah. So first, note that we maintain the tight edge. Yeah. The tight residual edge. The running time, like before, is mh plus u. Okay. So now it just remains to analyze what is u. And u is just the number of edge updates to the graph, to the residual graph. Okay. But you see that u is just proportional to the number of push. Because we're going to update this graph only when we send flow. And yeah, like when we send flow, we might delete some edge. We might insert some edge. Each push create like 1 or 2 updates to the graph. So this u is just proportion to push. Now let's bound the number of push. But like I'm just gonna like separate push into 2 types. The one that is saturating, meaning that you augment, like the amount of that you augment just equals to, yeah, this is actually I write CF of E. Yeah. You augment, like we have that like C augment is max of excess and the residual capacity, right? It's either saturated the residual capacity or not. Okay. That's the 2 type of push. Okay. when the graph has unit capacity, all push would be saturating because we send at least one, and this is one. So when the graph is, yeah, okay. So if the graph has unit capacity, you just need to bound this thing. Okay. Okay. Yeah, when the graph has unit capacity, all pushes are saturating. So now, here's a key claim. The total number of times that an edge can become saturated, that an edge E in residual graph can become saturated. No, actually, maybe I can say that like, yeah. An edge E in residual graph is at most H. For any edge E in residual graph, it can become saturated at most H time. How many edges are there in residual graph? There can be backward one and forward one. So the total number of edges is 2m. And each edge is saturated at most H time. So the number of saturating push is at most 2mH. Okay. We're gonna prove this just for each edge. It can become saturated at most H time. Anyone has some intuition why that should be the case? If I have this edge from U to V, okay. Once I saturate it, what happened? What happened to this edge in residual graph? I delete it. Okay. How can it become saturated again? It's not even there in the graph.
You had like reverse flow, like it got created again.
Exactly. Exactly. In order for it to become there, like to be reinserted again, the flow need to be sent in the reverse direction from V to U. Okay. And at that point, when we send flow from V to U, it means that at least the level of V need to be like more than U. So the level of V like is kind of at least U now. But for like to insert, okay. But then like if we want to saturate this, okay. If we want to send flow from U to V again, actually the level of U need to become more than V again too. Okay. So like each time that we saturate this edge from U to V, you need to at least relabel U. How many times can we relabel U? At most H time. That's it. So each edge can be saturated at most H time.
Yeah. Why does V have to go before U, before adding?
Because we only send flow through tight edge.
Oh.
So tight only go downhill. So we only like tight edges only go downhill. So it, like at least if V is here, it cannot go upward.
Oh.
So you need to relabel V so that it is at the level is like more than U or more than U and send in this direction. But then like to send flow from U to V, U need to be more than that level of V to send. Okay. So you agree with this? And so the number of saturated push is 2 mH. Okay. Okay. That's just what I said, but now we can conclude this. So the time for push level is just mH on unit capacity graph. Okay. Because the tight edge data structure have this much time, and this U here is basically mH2. Okay. Now, how about capacitated graph? Now we need to bound the unsaturated push. But this is where it's kind of getting worse. I can only say that unsaturated, like unsat push is at most mH square. Okay. Good. I will see if I have time to prove this at the end of the class. But for now, like, just note that, like, in this basic version of push Relabel, the number of unsaturated push can be actually as big as this, and we can bound it to be mH square. So it's not great. Okay. And the proof is using some potential function, but we have a way to improve this, so I'm just gonna go there. Okay. If I have time, I prove this at the end. Okay. But if you believe me that the number of unsaturated push is mH square, then the total time of push level is mH square in capacitated graph. And so that's the running time for to solve max flow. That takes mn square. Yeah. By the way, if you learn about, I'm not sure, maybe in some of algorithm class, you might learn blocking flow. That's another algorithm, and this is running time. The same running time. Anyway, we're gonna now see how to improve it. We want something like mn, not mn square. Okay. Okay. Good. So, okay. I'm gonna tell you now how to do mn square, mn log n, something like close to mn. And the idea is, like, I need one background, which is that we need the concept of top tree or link cut tree. It has many names in literature: dynamic tree, top tree, link cut tree. Anyway, okay. So what is this thing? You should think of this as, the name is a tree, but it's a data structure on top of trees. Okay. So what the setting is this. Let's say you have some forest. Some forest. It can be like rooted forest, like this. This is like a T1, T2, T3, T4. Okay. And we kind of try to build data structure on top of this thing, so that we can update this forest fast, and also can query something fast on top of this forest. Okay. And so morally speaking, this top tree data structure kind of will allow you to basically update and query anything that you usually want to do. It's not everything for sure, but like usually anything that you want to work on top of forest, that undergoes update, you can solve it. Yeah. And so I will tell you what does this data structure can do for our case, but it can do much more. Okay. So here's an example of update and query that it can handle. And basically, the cool thing about this is that every operation takes just login time. So basically, near constant time. You don't really need to think about it. So here is the example of update and query that you can do. Okay. So think like you have a forest collection of tree T. If I build top tree on top of this forest, then the update that I can do on this forest is, for example, I can link an edge. For example, if I have these two trees, maybe this two tree, then I can just maybe add an edge U to V. Then they become the same tree. The tree becomes connected. I can cut this thing, and now the tree has two parts. Now here's a cool thing. This is natural. It's like a basic, but this is the part that is quite non-trivial. Make this thing non-trivial. Okay. So every edge in the tree will have some value associated with it. So each edge each edge E has some value E, which is some number. Okay? Think of it as a number. And now, 1 second. Let me reopen this again. Okay, good. And now suppose that my tree is like long, like this. Okay. A long tree, many trees, but it's long. What I can do is like I can choose some node here, and I can choose some node here, X and Y. And what I'm going to do is just add a number, the same number along every edge on this path with value V. Like every edge along the path from X to Y, I just add this. The path can be super long, like N length. But actually, I can like maintain this value like implicitly. I can think like I add all this thing in log N time. Okay. So, and now what I can query is that, for example, look at this one first. I can check like, maybe let's say that I allow this thing, value E. Just return, like look at some edge, and then answer me the value of that edge so far. Because I might like choose many pairs of paths, and I might have like add the path here, add the path here, add the path here. Like I might like add paths many times, right? So the value kind of accumulated along many edges, but I can still query the value on any edge in time log N. Also, more generally, I can do this actually. What I can do is like, for example, I can look at X and Y, and I'm gonna return the minimum value along this path. That we can do. The path can be long, but you can still query this in log n time. So you see that this is non-trivial. Another thing that we're gonna use is just simple thing like given a node u, return the root. So if I'm here, then it's just gonna return the root of u. If I'm here, return the root here. Okay. Okay. So that's is the description of this operation clear? I will not tell you how. Like you can look up link cut tree data structure, and you can have a look. You can the simplest implementation is to use splay tree. There are some other implementation, but right now for us, just assume as a black box. Anything that you want, like this is like how I work actually. Anything that I want to work on the tree, I can do it. Assume it in log n time, can do it. Yeah, and usually we can. Yeah. Okay. So, by the way, like I think link cut tree is good, and you see that it's really good. Like this link cut tree or top tree is great in theory, but some people say that it makes things actually slower in practice. You need to ask practitioner. I'm not super sure. Like I know that some people in IOI in like programming competition use it, so it must be of some use. But yeah, I don't know. Yeah. But we're gonna use it in theory. Yeah. Okay. Now we are ready. Okay. The algorithm, we now call it tree push Relabel. Okay. We can initialize the same thing here, like before, but the new thing is here. I'm gonna maintain a forest such that for every node, there is not, For every vertex whose level, where level is at least 0, more than 0. Yeah. For every node that level is more than 0, just choose one tie edge out of it. If it's level 0, there's no tie edge for sure, right? But if it's level more than 0, then choose some edge, some tie edge that go forward towards level 0. So note that this is basically the same forest in decremental shortest path. In decremental shortest path, like everyone except T choose one tie edge out of it, and T has level 0. Here's the same. Everyone that has level more than 0 choose some tie edge out of it. So this is like a kind of shortest path forest, right? Okay. And what we're gonna do is like we maintain top tree on top of this forest, and we will make sure that the value, the value of an edge is residual capacity. That's what we're gonna make sure of. But know that in the beginning, this forest is empty, right? Because at the beginning, everyone is at level 0. But the graph keeps changing. Some node increase level, then there's gonna be this forest gonna appear. Okay. So now the algorithm is here. It's gonna be similar. Okay. As long as there is an active node, the one is not dead with excess. What we're gonna do? If U has some tight edge of it. Then we're gonna do three push. So what is this three push? If this node U have some tight edge of it, so maybe call it U2. Previously we just pushed to U2. But now we know that U2 have some tight edge of it. U3 have some tight edge of it, if it has. Okay. So basically we look at the forest, this forest T. And like this forest will have some, like if U is in the forest here, then this is a tree containing U, and this is like a root. This is root of U. If this is the root of U, then this node have no tight edge out of it. Otherwise, like it's not a root, it would go further. Okay. So we have this tree. Okay. And the idea is that instead of pushing just one, yeah, why not just go all the way to root? We wanna reach the thing as fast as possible. And that's so intuitive that this is all shortest path. Just send along the shortest path to the root as fast as possible, right? To the sink. So we send from U to root. Okay. So how much we should send? We identify like before, how much we should augment. The access at U, we don't want to send more than 8 access. That's like before. But then how much should we send from U? I'm just gonna query this thing. Okay. And this is supposed to be basically the minimum of from, let's call this path P, edge along the path. The residual capacity. Right? Because we maintain that the value of each edge here is the residual capacity. So just look at all of these edges. Take the guard that has minimum capacity. Because if we send more than that, then it's not possible. We want to send like as much as we can. So this is the bottleneck. So like we look at my access and the bottleneck to the root. So that's the amount of flow we want to push. And then what we do, we basically push this many units of flow from U to the root. What does it mean for the data structure? We just take this path from U to root of U and reduce the residual capacity by this much. Just like before. Does this operation make sense? 3 push.
Do we have to update the backwards edges too, or is that about the residual?
Good. So we will not do that actually. Yeah. I talk about this specific thing soon. But so far, right now, just think like you are totally right that like if we kind of say that we push through this thing, it seems like we need to add backward edges along everything here, and that seems like a lot of work. We don't want to do that, and we will not do that. But I'm gonna say that it's actually fine. Okay. Okay. But for now, you can think like magically you can think like magically we do that too, and suppose that it's fast. But actually, we will not do it, and to make it fast. Yeah. Okay. So that's what we do when there is some tight edge out of U. But if there is no tight edge out of U, just relabel like before. And then we just return the flow. Okay. And I hope you see that like This algorithm just is the same algorithm, except that we kind of shortcut several steps. Instead of send the flow step by step, just send it faster. So the correctness is going to be the same. Like, it's going to compute maximum flow like before. It's just faster. Okay. And yeah, instead of push through a single edge, just push through the whole path of tight edges. And to compute max flow, just do the same thing. Correctness is the same. What we need to do is just to analyze how fast this is. Okay. Now is the thing that that I like. The topic, like the thing that Lucas just pointed out. Okay. Some details about implementation here. Like, we used to do such, like what we used to do is that we used to maintain residual graph explicitly at all time. But now the residual graph will not quite correspond to the flow exactly. How? Actually, for any edge, like all edges outside the forest T, we maintain residual graph explicitly. Explicit. So everything outside the forest actually is still good. Okay. But only edge inside the forest, it will not like correspond to the like we will not like have we will not maintain we do something that is a little bit off. How exactly? Let me tell you. Okay. So maybe think like this. If this is like a tree, okay, and let's say that we push flow from U to root U. Maybe from A to root A. Do this. But now look at some edge U and V. That's this edge U and V in the tree. Okay. So after we have pushed flow through this edge, suppose that we push flow through this edge, we will not immediately add this reverse edge. That's what we don't want to do. Okay. Because if we do it, like, so okay, we will not add this reverse edge, but we will add it only when UV is not in the tree. So, for example, if this edge UV becomes saturated, then it shouldn't be in the tree. That's only when we add. Only then we add this edge from V to U. Or like if the level of V need to be increased, so this edge is not tight anymore, so we add this edge from V to U. So basically, some backward edge from V to U will not add it, but we just remember like that kind of we need to remember that okay, we didn't add this backward edge. But whenever UV is kind of kicked out of the forest, then we remember that we should have added and then add it only when like U and V is not in T. That's all. Like that's what we didn't do. Yeah. Just remember we should have done it and do it when we need to do it. Why this is okay? The fact that we didn't add an edge from V to U, that's okay because as long as there is an edge from U to V in this tree, we will never use this edge from V to U anyway. It's like there's no way, it's not useful. So it's okay even if we don't have it. But whenever this guy kind of kicked out of the tree, UV is not in the tree anymore. Now we remember we need to do it and we do it. That's it. Okay. Okay. So that's what we not, like that's how we didn't maintain GF explicitly. So next, what's the total number of edges, edge update to GF? The total number of edges to GF, which is U, I now claim that it's just at most the number of cuts. Okay. So why? Because when we cut U to V from the tree, that's when you kind of remove this edge from GF and you might add also an edge from V to U. Okay. So that's it. Like we update GF only when we cut. Like we do cut operation to the top tree data structure. Okay. So U here is just at most the number of cuts. So we now kind of need to analyze how many cuts we have. Okay, so now let's analyze the time. I show that the total running time is something like mH. Okay. So first, let's bound the number of push. What the number of push? There are two types again. The saturating one. The saturating one, there are mH at most, like before, because just like before, yeah. Okay. How about the unsaturating one? Okay, I claim that it's going to be at most NH, even less than mH. Why? Because suppose that we do unsaturating push. Like the fact that we do unsaturating push, basically we send the excess, right? There's no bottleneck, so we send my total excess from U to the root. So my total excess will become 0 after pushing. That's when it's like when there is no edge saturating, my excess become dry, become empty. Okay. But once this thing become empty, it means that node U become inactivated. It's not active anymore. And I claim that each node can be inactive at most H times. Why? Well, like, suppose that a node here become inactive. Suppose that you have no access anymore. It's 0. Okay? You have no access. How can you become active? You can become active only when there is some access at you. But the way that the algorithm goes is like, maybe there is like some guys that connects to you and might send flow through you. Like, if the flow sent through you, there's no access at you, because the flow just sent through it. Okay. So you can become like, okay, 3 push will only send flow through you, okay, until if it doesn't send flow to you, only when there's no tight edge out of you. So you actually become the root. That's when like some guy might send flow to you, and then like the access kind of end at you. That okay. So when you become a root, you might have access. But if you it's a root and it has some access, what will happen? There's no tight edge of you, so you will just relabel you. So like in order to send flow out of you again, like now view is a root and it become active. But to send flow out of you again so that it become inactive again, you need to relabel you. But you can relabel a vertex at most hash time. So you can become inactive again and again and again at most hash time. So that's why you have this. So, okay. So the number of unsaturating push is the most number of inactivation, which is NH. Okay, which is the most MH. So that's the number of push. Okay. So now we are almost done. Let's count the total number of operations that we do on the top tree. We might add path. We might like call min path. That's we call it once for tree push. Like for each tree push we call it once, but tree push is at most MH. Okay. How about cuts? Number of cuts? Well, we're gonna cut an edge from the forest if some edge become unsaturated. That's like it need to be deleted from the residual graph. So that's when we cut. Or if some node is relabel, okay, we like some guys used to be tight and it's not tight anymore. So we're gonna cut all those edges that is because of relabel. Okay. But the number of edges that become saturated is at most MH. We learned this. The number of edges that is cut because of relabel, well, we relabel for each node at most hash time. And edges, like we might cut all edges that we relabel, like so that's we pay degree. But even this is at most MH. Okay, so cut is at most MH too. How about link? Number of links is at most number of cuts plus n plus 1. Why is that? Because like you start with empty tree. So like if you keep, so okay, the number of edges in the forest is at most n plus 1. So you might keep linking, but you cannot keep linking more than n plus 1 until you cut something. So number of link is at most cut, number of cuts plus n plus 1, which is the number of cut is at most MH. So all this means that top tree data structure takes MH log n times. Because the total number of operation here is at most MH. Okay. How about tight edge data structure? We have this running time. But we've seen before that, we've seen before that number of edge update is total is at most 2 number of cuts. That's MH. Okay. So that's why the total running time, like we basically have the 2 data structure, and each of them, one takes this much time, one takes this much time. So it's at most MH log n. Okay. Questions? So the point is like push through the tree faster. Okay, so I didn't prove the bound for mh square, but you can have a look. It's simple. And also another thing that I didn't show you is like, what if we want to find minimum cut instead of, we get maximum flow. What if we want to cut? Okay, I didn't tell you that, but you can have a look. Yeah. Any question before we finish today? Okay. Yeah. So next class, we will go beyond computing max flow exactly. We're gonna compute it approximately, but faster than MN. Okay. Yeah. So we might maybe let's see next class. Yeah. See you.